the format that we adopt. So can people see the screen?
Yep.
Yeah.
Perfect. Before I begin, thanks as always to the organizers, all the other speakers, everyone who made this a really great Zoom meeting, because that is definitely not an easy thing. Especially to get this level of discussion over Zoom is kind of amazing. In this talk, I'll be pretty brief. Initial data is, as always, kind of a more self-contained topic than a lot of the ones that we're talking about. There honestly isn't necessarily as much physics going on that needs to be captured for initial data. But I did want to kind of highlight some of the things that came up in discussions, especially way back when on Monday, plus some of the other things too. For initial data, because it's a single slice in time, it's a much more, I don't know, practical kind of application. It's there to do a job in a lot of ways. The secret is, in a lot of ways, write a code or codes that get that job done as much as possible. It's become very clear from the past while that the current initial data codes are particularly good at dealing with, at this point, virtually any equation of state you can choose to write down. And that also means different ways of formulating that equation of state. You don't need to deal with really any serious evolution aspect of your equation of state, even if it's not uniform in temperature, as long as you can specify some rule for the temperature distribution. In theory, what you're really looking for is, at the end, pressure as a function of density. So you can tabulate it, and the codes can do this. You can use polytropes, and the codes can do that. One thing that I haven't seen mentioned recently, but I remember this from a talk a couple of years ago by Richard O'Shaughnessy. I think one thing to watch out for, there's always been a little bit of a disconnect between some of the LIGO data analysis community and the numerical relativity community as far as how things are formulated at times. In talking with Richard O'Shaughnessy, it came out that the way that LIGO people often view piecewise polytropes doesn't always agree with the way numerical relativity people do, as far as how you get around the corners where the polytrope changes behavior. But certainly at this point, any functional form for the equation of state will do. Binary initial data codes are also very good at this point at dealing with arbitrary mass ratios. We heard some of these in the talks that just happened. I was already to say the talks that are about to follow, but because of the schedule change, we heard about mass ratio being an important thing to get right. Mass ratio doesn't sound like much, but in some sense, after the chirp mass, the mass ratio is pretty much the second observable you can really hope to constrain from the decade worth of gravitational wave data and everything else we're about to see. A lot of these other measurements that are extremely exciting require more fine-grained analysis. The masses of the two neutron stars in the end are probably the first and second measurement you're likely to get from a gravitational wave observation. There's active work now going on kind of the second level of physical inputs you can put into an initial data code. Magnetic field configurations, there is starting to be work on kind of how to properly put a magnetic field into a binary neutron star calculation. The question is, what is the proper configuration? What is the reasonable field strength? There's also a question as to how much exactly this will affect the later evolution, but evolution has many stages. There's the gravitational wave signal, which is primarily going to respond to the bulk features, but some of these ejective properties are going to be more finely affected by the smaller scale dynamics, the stuff coming from some of the lower density regions that are more likely to feel magnetic forces than the bulk of the neutron star material. Um, One thing certainly that might be of great interest, given how much this whole meeting has focused on the issue of disk dynamics and the different processes leading to different kinds of ejecta, would be the role played by neutron star spins. The lore has always been, especially from the gravitational wave side, that the neutron star spins aren't likely to be so significant. But when you're talking about dynamical ejecta, especially from kind of the outer regions of the neutron stars, the spin states leading into merger, this is something that needs to be explored in more detail. So certainly initial data needs to be able to handle some amount of neutron star spins. As far as I know, there's no particular reason to assume that spins have to be aligned. So we're talking not just aligned spins, but misaligned spins in these cases. And even if you want a second order effect, there are more rigid body kind of spin approaches, or even potentially differential rotation, depending on what we believe about the state of neutron stars. To get into some of the issues that were raised by the various speakers, I thought it was really interesting that we heard somewhat similar comments by Masaru Shibata and Cole Miller about very different stages of the evolution. Masaru Shibata pointed out that in order to explore the post-merger regime for binary neutron star mergers, it's probably something at the exaflop level to get the problem really done properly. Something, I don't remember if he said exaflop, but it's a very large amount. This is a computational challenge for the next decade, as he posed it. Cole Miller in the Monday afternoon discussion was talking about how in order to examine some of these pre-merger mode couplings, you might want resolutions down to something like tens of meters for your neutron stars. What struck me as interesting is that the configurations are very different. Merger into post-merger, you've got a very complicated hydrodynamic state, especially during the merger itself. Pre-merger, sorry, I didn't have a chance to prepare slides, so I'm gonna have to go with a visual demonstration. Pre-merger neutron stars look like this. And if they're farther apart, they look like this. And if they're closer, they look like this. And maybe there's a little bit of tilting, but that's about it. It strikes me that if you're talking about pre-merger calculations, it's not clear that even if you need resolution, just trying to do it in a 3D sense, maybe trying to solve a problem using a familiar tool rather than the right tool. Neutron stars prior to merger are extremely simple objects. They don't have that many kind of true physical degrees of freedom to deal with. Merely resolving them to death might be an indication that there are other kinds of approaches that could help with the situation. And certainly with initial data, that's kind of the approach you might expect that kind of spectral approach to describing your neutron stars is probably closer to what we need to attack some of those problems than maybe necessarily just everything with just increasingly large 3D grid-based simulations. Zach Etienne in his talk, in a discussion on Monday afternoon, was talking about how gravitational wave errors accumulate during the final in-spiral phase for the merger. There's definitely some work to be done in kind of working out best practices for the ideal starting point for binary neutron star simulations. The big difference in some sense between neutron stars and black holes, error in black hole initial data, and this is a cartoon, someone please correct me if I'm wrong. The spurious terms, the unphysical behavior is typically radiated away in that initial burst of junk. And then the black holes will largely settle down into a different configuration possibly than the one you wanted, but they will kind of relax themselves towards some kind of different state. Neutron stars, because they're hydrodynamic in nature, the errors can lead to shocking, and they don't necessarily relax into some nice state. In some sense, your initial errors can continue growing as you go through the initial phases of a dynamical simulation. So it's not clear that just running for longer with neutron stars is better. And it's possible that if you start them too early and your dynamics aren't accurate enough, they'll continue to move away from the state that you want them. Jake Lang on Monday talked about how binary neutron star gravitational wave data analysis is typically performed using binary black hole effective one-body models with tidal corrections rather than binary neutron star initial data itself. So binary neutron star initial data is used to inform some of these things, but it's kind of not used directly. If you think about how long it takes to do an initial data simulation, the longest ones basically take about a day on a single processor because they're typically not parallelized in any particular way. It is possible to come up with extremely large data banks of initial data. So they may have a role to play in some of these, at least informing data analysis, hopefully at some point in the future. I think it's certainly true that the field, because initial data is a smaller problem, the field benefits from initial data on demand, either large banks of initial data ready to go or the ability to generate them quickly. There's definitely been some work out there that would argue that you need to be careful with robustness checks, comparing codes, resolution aspects. Just because initial data are generated for a given configuration doesn't mean that when placed into a dynamical simulation, they'll all run the same. So this is definitely going to be, the robustness checks are always important. This is going to be an important thing for the field going forward. Making sure that we understand the systematics that go into the initial data generation. And of course, kind of looking forward, every issue discussed here, only gets more interesting when you start talking about black hole neutron star initial data, which is clearly where a good bit of the computational work is going to continue to go in the future. So that's kind of the summary of what we heard way back when on Monday. And I'm happy to throw it open for discussion. I was trying the famous result that judges give harsher sentences right before lunch may or may not be reproducible, but I figured it was safer to try to keep this short regardless.
Okay, thank you, Josh, for this nice review on this problem and sharing your thoughts about some of the talks in this workshop. Let's thank the speaker by clapping the speaker, and we are ready for questions. Julian, did you have your hand raised for this talk, or do you have a question? Okay, if not,
sorry, that was a leftover. Sorry.
Oh, okay. I was imagining, but I do have one follow-up question for Josh. I think one of the outstanding issues that we have with initial data is that we are all using pretty much the same initial data that are available publicly, the Lorraine data. So there are other initial data solvers out there, and I know, for example, Wolfgang Tichy is working on some, and there might be plans, and which includes beams as well. So I'm wondering, whether there will be in the community a little bit more attention toward generalizing and making this data publicly available, because I think it's where everybody starts, right? So right. It's very limited what we've got so far.
Right. I mean, certainly with the TCAN project, we've been kind of releasing it. I think there's reason to hope that initial data, I think, is seen as much less of a trade secret and much more of just kind of a tool than a lot of the dynamical simulations and codes. So ideally, yes. I think in some ways the missing piece is I hesitate to say this, but almost software engineering and things like that at this point. One of the secrets is, or one of the useful tools will not be so much just libraries of initial data as much as the ability to essentially download a code, specify a handful of parameters, and pretty much, generate your own. It can be done on a laptop. So honestly, for the field, this is one of these ones where ease of use probably matters as much as as making the data public too. I'm reminded by Zach Etienne's efforts to kind of make a lot more codes, not just public, but user friendly as well. And,
Right.
and many other people too. This has been a trend. For initial data, I think it's particularly bad.
Yeah, so that's one. And waiting for other questions, I may, Vasilios, but since I have this question on the top of my head, and then Vasilios. Well, actually, let's go with Vasilios. I think I will ask later. Yeah, go ahead. Vasilios.
Hi, Josh. Very nice summary. I had one question about the exaflop, or in general the exascale, and where our field is going to go there. So if I understand it correctly, or I don't know, making some calculations in the head, I think with GMHD and just increasing the resolution, you might get to where you need exascale machines or exascale simulations, but the problem is increasing the resolution also lowers the time step, and you become wall time limited, right? Nobody's going to give you an exascale machine to run for 2 years to make your ridiculously high resolution neutron star merger. And I think in the supernova community, at least, people starting to get away with that by basically the radiation transport, or the neutrinos are the thing that costs the most, but then they still simulate for roughly the same wall time. So I guess what is the feeling in the field of what needs to be done there? I think Carlos made the work that Carlos has done with doing subgrid models. I think that might be a very interesting application, where you have like a really short, really high resolution simulation that you then use to inform subgrid models, and then you can apply for InSight proposal or something and do ensemble simulations where you run hundreds and thousands of binary neutron star merger simulations on an exascale machine. But I don't really see that one big exascale simulation with the current infrastructure. And so I guess just maybe steer some discussion what people feel about that.
I mean, I can't answer for everyone in the field doing the dynamic simulations. I'm sure people have thoughts. One thing I think that's critical when you start to talk about that scales is using a code that's very well tuned for the physical problem. For initial data, or maybe even some of the pre-merger regime, a 3D grid-based code isn't a geometry that corresponds to the problem at hand. These either multi-domain spherical methods, or things that kind of target the grid structure to the problem itself, can get you huge efficiency gains. It's I'm sure with your talk on with the talks on multi-patch and spherical GR, codes that are tuned to the problem at hand can give not just efficiency gains, but orders of magnitude efficiency gains if you tune them properly to the problem. The second that you're talking about petaflops and exaflops, that becomes absolutely critical. I don't see how we get away how we get away from it.
I agree, but I mean, Zach was talking about running binary black hole mergers on a desktop, right? That is the complete orthogonal direction to when you want to get an InSight proposal at Summit, or later on Frontera, where you basically have to show that you can use the machine at scale, right? You're not going to say, instead of running on my desktop, I want to run on 100,000 desktops on your machine. So I don't know, from the point of view of here at Oak Ridge, I guess I kind of want to reach out to the community and ask them what their thoughts are going in that direction. I don't know what the future is. There might be that CPU clusters will stick around, and NSF will continue to fund and build CPU clusters, but at some point, I guess, maybe there has to be a paradigm shift. I don't know. So I guess.
Yeah. Well, I think, we will not all have access to, the machines that Masaru has access, or maybe you have access, at the DOE labs, but, so I think we'll have to adopt something like Carlos is adopting, although I think that there will be more testing that need to be done, and really we need to understand, in which circumstances, we cannot use cut loss subgrid models ideas applied to the various situations we have. So I think we'll come around in the next decade with probably a mix of both, right? But before I close and pass to Julian, because I think it's late, just a quick comment to Josh about this public initial data repository and the fact that it was proposed by Caroline that we could parameterize the equational state to allow a better, to allow us to better study the equational state. Perhaps this also finds some room for generating the initial data, providing equational states with such a parameterized formula.
Mhm.
So I don't know what you think, Josh, but that was a comment, not that necessarily you need to follow up.
Thankfully the equation of state stuff has become pretty well advanced and in a way that's easily reproducible, as long as the model can be described properly. Then I think the equation of state is now the easiest part of your typical initial data scheme. Basically, if someone can look at the other hydrodynamical variables and identify what the pressure should be, it can pretty much be put into code. The initial data schemes are much more agnostic about how it's constructed than a lot of the dynamical codes at this point.
Okay. So, well, thank you. I think we should move on to the last talk of the workshop, and the last talk will be given by Julian Krolik, Johns Hopkins University. Julian, are you? Yes,
Yes.
you're on.
Yes.
So you're good to go.